All right, hey friends. Miss Willis here with your Honors Pre-Calc Unit 3, Day 2, Graphing Rational Functions video. All right, we're going to jump right in. We're talking about different things about the graph, okay? So here is a review of discontinuities. It might not be a review, but hopefully you heard some of these discontinuities before. So there's 4 different types. We have, of course, a continuous function. And that is where all x values are defined. Where all x values are defined. That's a continuous function, okay? And then we have a removable discontinuity. And that is where the general limit exists that is where the general limit exists, or aka a hole, because even if there's a hole, the general limit still exists, okay? And so general limit, remember that it has to approach that hole from both sides in order to be a removable discontinuity. So the graph, technically it can be fixed if I put that hole right back, like it would be a continuous function. So a removable is just one little small portion of the graph is gone. So the next one is, so maybe we should draw a picture before I get started with that. So a continuous function, again, something that you can trace with your pencil and it's never broken. Okay, a removable discontinuity would be where like there's a hole and it would just keep going. Okay, that's removable. Because that's different than a jump discontinuity. And that is where both one-sided limits exist, but have different values. So both one-sided limits exist, but there's a different value for both. So a jump discontinuity, if you were looking at a graph, it might have a hole, but then it jumps down to somewhere new. So I can't fix this graph, so it's not removable. If you can't fix it by just filling in that hole. So with removable, I could just fill that hole right there in. But if I filled in this hole, that doesn't fix anything. So jump is when you can't fix it and they equal different values with the one-sided limits, and removable is you can fix it with that by putting in that hole. All right, so, and then the last one, it's got 2 words. It could either be called, let me use my right color. It could be called an infinite discontinuity or a asymptotic discontinuity. Okay, so an infinite discontinuity is where both one-sided limits are infinite. So they're both going to infinity, whether it's positive infinity or negative infinity or whatever. So what would that look like? It doesn't look like a jump. Those aren't going on forever at that jumping spot. So like with a rational function, it has an infinite discontinuity or an asymptotic. I don't know how to say that as well. So I'm going to use the word infinite. So right there, where that asymptote is, would be where my infinite discontinuity. So it's a difference between a jump. So I'm going to draw a picture of a question that could be on this. So you're going to need to draw a graph. 3, 4, 5. Let's just go to 5 on the x-axis. Or 6, however many I went to. So I'm going to number them. -1, -2, -3, -4, -5, -6, -7. 1, 2, 3, 4, 5, 6, 7. All right, so let's draw. So this picture, have it stop here at 4, and then come and continue down here, and go like that, and then so just draw this picture, okay? So I might ask you to state all the different types of discontinuities. So starting here at x equals -4, I have a jump discontinuity. X equals -4 is a jump discontinuity, okay? At x equals -1, so right here, both are going to infinity on both sides. One's going to positive, one's going to negative. So that is either an infinite or asymptotic discontinuity. Okay, and then we have right here at x equals 3, we have a removable because it just, all there it is just a hole there. Yes, there's a hole at x equals -4, but it jumped up. These just continue right after the hole. There is no jump. It's on the same level. So it's x equals 3 is a removable discontinuity, or a removable hole is what some people call them. So a removable hole. And then that last one, let's do this right here, is another jump discontinuity. So I have 2, so I'm just going to put x equals 5 and x equals -4 are jump. Okay? Everything else is continuous. So you don't usually state, oh, it's continuous from here to here. You usually say what's wrong. What kind of discontinuity is it? All right. Next problem. We are going to do review of domain and range without a calculator. Review of domain and range without a calculator. All right, so here's the example. We have f of x equals x squared minus 6x plus 8. And then we have negative 2x squared plus 10x minus 12. All right, so when we're doing domain and range, we need to know the holes, vertical asymptotes, and the horizontal asymptotes, okay? So in order to do that, we did that last class, so pause the video. I would like you to factor it and see if you can figure out your holes, vertical asymptote, and horizontal, because that's what's going to cause issues in my domain and range. Those are the values that are undefined, all right? So welcome back. I hope you've answered those questions. If we look at this before I factor, I'm going to look at my horizontal asymptote. So based on the degree on the top and the bottom, those exponents are the same. So this is EATS DC. Exponents are the same, divide coefficient. So my horizontal is y equals -1/2. Because my exponents are the same, so I divide the leading coefficients in front of those. Okay? My holes, I hope you factored, and you should have got x minus 4 and x minus 2 on the top. And on the bottom, you should have got taken out a -2, and then you would have been left with x minus 3 and x minus 2 when you further factored it. So I have a hole right here. So I have a whole at x equals 2. So that's part of my whole. I'm going to cancel those. To get the other part of the whole, I just plug in that 2 to the remaining part. So 2 minus 4 on the top, negative 2 times 2 minus 3 on the bottom. So I get negative 2 over 2, so negative 1. All right, and then the vertical asymptote is what is remaining in the denominator. So that x minus 3. The 2 doesn't matter because it doesn't have a variable, so it's not going to cause any issues. So it's just x equals 3 is my vertical asymptote. All right, so let's write the domain and the range. So domain, remember, is x values. So the x values that are causing issues over here are 2, it can't be 2, and it can't be 3. So we write the domain. Those are the x values. So it would be everything but negative infinity to positive 2, union 2 to 3, union 3 to infinity. Why am I not using brackets, guys? It's undefined. Remember, wholes and asymptotes are undefined values. They're discontinuities. They are not defined on the graph, so we can't use brackets. So for range, where is it undefined for the range? Well, the range is undefined at negative 1 and at negative 1/2. Those are the y values that all my undefined values happen at. So we would say negative infinity to negative 1 union negative 1 to negative 1/2, because I'm putting these in order from least to greatest, or it's wrong, negative 1/2 to infinity. Now, I could even ask you, okay, well, what type of discontinuities do I have? Without looking at a calculator, well, we have a whole at 2, negative 1, so that's going to be removable. We have a removable whole at x equals 2. And we have an infinite, because that vertical asymptote is what causes it to be an infinite discontinuity. So I have an infinite discontinuity at x equals 3. So these right here is if I asked you, what are my discontinuities? There's nothing else, okay? A jump would only happen in a piecewise function. We're not doing piecewise, so here we are. All right, let's keep this train rolling. You'll practice them in class. So hopefully that was enough. So here is what you need to graph, because that's what you're going to do. We're not going to graph any in this video, but I'm going to set you up on how we got to be able to find everything. What you need to graph. Okay? You need 6 things in order to graph. Okay? The first thing is you need to know what your holes are. Okay? And that's written as x comma y. And in order to get the holes, we're just going to put a little blurb. You have to factor, cancel, then plug in. Okay, so that's number 1. Number 2, we need to know the vertical asymptotes. And that was going to be written as x equals whatever number. And what is a vertical asymptote? It's what is left in the denominator after you cancel the holes. After you cancel the holes. So reiterating this as well, guys, you can't be a whole and a vertical asymptote. It's one or the other, okay? This is not a double dipping type of deal. One or the other. All right, number 3, you need to know your horizontal asymptotes. Okay, that's y equals a number. And how do I remember that? That's Bobo, Botan, and Eats DC. So Bobo, bigger on bottom, equals 0. And then there's Botan, bigger on top, equals none. And then there is Eats DC. Exponents are the same. Divide coefficients. Okay? All right. here are the 3 other things. We found all those before. The other thing you need to know is if there's any x-intercepts. And those are written as a number, comma 0. And all you have to do to find the x-intercepts without a calculator is set the numerator equal to 0 as long as it is not a whole. Okay, that's how you find the x-intercept. All right, so what that means, so if I look at this problem, my x-intercept is x equals 4. So 4 comma 0, because that's the only thing remaining in the top right here. This guy is an x-intercept. Not the x equals 2. Can't be a whole. Well, it can be a whole and an x-intercept, but it's not because it doesn't cross at 0. But sometimes it might, and so then that's just a whole on the x-intercept. Okay. Number 5. You need to know the y-intercept. And that is written as 0 comma a number. And all you have to do is plug in 0 into x. And you can plug it into the factored version or the original version. I think original is easy because if I plug in 0 to the original version, looking back up at this example, if I plug in 0 there, then my x's are gone, so I'm left with 8 on the top and negative 12 on the bottom. So my y-intercept would be 0 comma 8 over negative 12, which is negative 2 over 3, right? That's the y-intercept. Easy, all right? You can't have more than one y-intercepts. You can have more than one x-intercepts, but you can't have more than one y or it wouldn't be a function. All right, last thing, and brand new, last thing we're going to do in this video is you have to know there's 3 different types, and I think I warned you in the last video, but there's 3 different types. The in-behavior asymptote. And I really hate spelling, so I don't write that. I call it the EBA, just like I did with vertical and horizontal. Okay, so when does the EBA exist? Okay, in behavior, so horizontal asymptotes are in behaviors. Okay, so when there's none, we have an in behavior asymptote, but it's different than the horizontal because there isn't a horizontal, but something's controlling the ends. So when does the in behavior asymptote exist? So if it's Bobo and eats DC, so if it's bigger on bottom, it equals 0, dividing coefficient, if it's those 2 right there, then the EBA is equal to the horizontal asymptote. So if it's 0, it's y equals 0. If it's the exponents are the same, so on this problem, my exponents were the same, y equals negative 1/2, that is my in behavior asymptote. But there still exists one when there's none. So if it's Botten, in order to get the in behavior asymptote, you have to do long division to find the equation. Sometimes you can do synthetic, but sometimes you can't. So I always do long division. You have to do long division to find the equation. And the equation is everything without the remainder, okay? No remainder when you're finding that. So let's do an example. 2 examples, and then we're done. So, find all asymptotes. That's all of them. So now when I ask you to find them, we got to find horizontal, vertical, and in behavior. So 3 different problems. So here's the first example. F of x equals x cubed over x squared minus 9. Okay, so I need to find the vertical, I need to find the horizontal, and I need to find the in behavior. I would pause and see if you can find at least the first 2. Okay, so x cubed doesn't factor. The bottom is x plus 3 and x minus 3. So I don't have any holes. So then that means that x equals 3 and x equals negative 3 are my vertical. The horizontal, so what is this? It's bigger on top, because 3 is bigger than 2. The degree is bigger on top, so that means there is none. The in behavior asymptote, so that means we got to do long division. I wouldn't have picked a problem without doing long division. All right, so this one's easy. X squared minus 9 on the outside, x cubed on the inside. We need to think to ourselves, okay, how the heck does x squared become x cubed? Well, you multiply by x. So then I get x cubed minus 9x. So let me put my little placeholder here. And then I subtract. I could have put a place, well, you're probably like, well, what about x squared? I don't need a placeholder for x squared because I didn't produce an x squared. So this is gone. 0 plus 9 is 9x. So can x squared ever be 9? No. So my in behavior asymptotes, what are happening is this is y equals x. That's the in behavior. So the linear line y equals x is controlling the ends of the graph. Okay, so that means I have something, that probably, let me get my, because I'm thinking what's happening with those in behaviors. I know I have 2 vertical asymptotes happening here at 3 and at negative 3. So this one's going to be a funky looking graph. So we got to figure out what is happening. If you didn't have a calculator, then you can, but you can kind of guess what's happening. I have, my graph is going to be here and here on the ends, okay? And then the middle is happening like that, okay? There's something happening in the middle. I just didn't know how that was going to look. That's why I grabbed my calculator, okay? All right. Let's do another one. Last one. F of x equals x cubed plus 2x squared plus x minus 9 over x minus 3. All right, we need to factor this first. Well, if I type that in, you wouldn't be able to factor this one without a calculator because it doesn't group. X cubed plus 2x squared plus x minus 9. And if I hit graph, it doesn't look like it has a good perfect square, or at least it doesn't have one with 3. So it's not going to cancel out 3. So we're not going to even bother factoring it. If the only reason you're factoring is you're trying to see, well, is this a whole? It's not, because it's not even a factor of the top. Okay, so my vertical then is x equals 3. My horizontal is bigger on top. That equals none. Bottom. So that means I have to do long division to find my EBA. Okay, let's do this. I guess you could technically do synthetic division for this guy. So x minus 3, x cubed plus 2x squared plus x minus 9. All right, so if you could do synthetic division. I couldn't do synthetic division because of that x squared. So if it's just a 1x minus 3, yeah, do synthetic division. But you got to do something in order to get that in behavior. So x times x squared, and then I multiply. And I should have checked. Let me double check. Do I have all my degrees? 3, 2, 1, none. Yeah, so I don't need any placeholders. So I subtract, which means change the signs. 2 plus 3 is 5. X times 5x equals 5x squared. So then I multiply. I'm going to drop down my x. I multiply, I get 5x squared. Negative 3 times 5x is negative 15x. And then I change my signs. These cancel. X plus 15 is 16x. And then I drop down negative 9. X times 16 is plus 16. So then I'm left with 16x plus 48. Well, these are gone, and then I don't have any x's. So that's going to end up being my remainder. Okay, so I don't even have to worry about that. So because the remainder is not my end behavior asymptote, just what goes in evenly. So the end behavior asymptote is that whole quadratic equation, y equals x squared plus 5x plus 16. So it's actually a parabola that's controlling those ends. Okay? All right, ladies and gentlemen, it's been real. I hope you enjoyed this as much as I did. We're going to be graphing it in class. When you see me, Miss Marshall, or Miss Fisher, it's going to be a fun time. Bye!